Yes, we were discussing the extrusion-based systems in the previous week. We discussed the fundamentals. We have watched some videos, and I would like to show you another one, a nice one, a bit different than the conventional desktop printers. Now I will share it with you in a moment. Let's share presentation. Yes.
2013, President Obama said, 3D printing has the potential to revolutionize the way we make almost.
So this is actually the main difference. As you see, they don't have any kind of a Cartesian X, the conventional X, Y, and Z coordinates. This is a bit tilted. This is again our extruder head. This time it's not printing on an XY plane. It's printing on an inclined plane like this, about 45 degree of angle here. And the advantage of this approach is that this is the building plate and it's moving. It's a kind of a conveyor belt. It's moving in this direction continuously, which means that with this approach, with this inclined plane, you can have continuous material extrusion. This is a very suitable approach, especially for mass production. And you can also see similar items here, the fans. They are for cooling, and they have a special bed. I'm not sure whether this is heated or not, but it has special patterns so that the material can easily stick to this conveyor belt.
Revolutionize the way we make almost everything. Indeed, 3D printing has become a technology that will change the way we produce things. However,
they can easily produce such longer products. They don't have a specific build volume. They have some limitations from the size, but for the length of the part, they don't have any limitation.
However, there are still challenges that prevent 3D printers entering the industrial landscape. Black Belt 3D has addressed these challenges and
You can assume that this is their kind of X and Y axis. Obviously, it's inclined, but their fundamentals are the same. The main difference is actually on the bed side. It's moving all the time, not stationary.
Started from scratch to redefine.
So you see they have a huge part. This is their name, Black Belt 3D printer. They have printed this part in a single operation.
Fused filament fabrication technology. We are proud to present you the Black Belt industrial production platform. But what is so special about this new printer?
Hi, my name is Stefan Schirmer. I'm an inventor and industrial design engineer. The past 2 years, my job was to apply 3D printing to industrial applications, but the limiting factor was always how the existing technology works. That's why I have developed the Black Belt. This new patent-pending technology is not only capable of manufacturing very long products with unsupported overhangs, but also to mass production right away.
Yes, you see an example of mass production. Since this conveyor is always moving, we can print many products after each other. And you don't need to restart the printing process since it's already sliced. It's probably using the same motion data, just this belt axis is moving.
By the way, which is a breakthrough in terms of 3D printing. Imagine what you could be producing with this new production technology. Together with selected experts in metal conversion and assembly technology, we have engineered a production-ready machine using industrial quality parts. This is not just a concept. We have developed a market-ready machine that is tested and ready for production. We have decided to launch on Kickstarter to be able to finance the first production run and to develop a user-friendly slicing software that goes along with the Black Belt 3D printer. This is why we are reaching out to support our project, allowing you to become first in your industry branch, applying this state-of-the-art disruptive technology.
So this is a nice example of for mass production. Now I will show you another example. That's a bit different. Yeah, this is called as programmable filament. So what they are doing is that they first print the filaments. In the previous week, I said that usually at the back side of the printer or beside the printer, we have spools of filaments, especially for desktop fused filament fabrication printers. But now they are following a different scheme. They have a different paradigm. What they are doing is that by using a printer, they are printing the filaments. And the thing is that they are printing colored filaments by simply changing material from time to time, and they need to join these colored portions properly. And then what they are going to do is that they will remove this printed filament and use that printed filament as the new filament of the next print. With that approach, they are actually printing some colorful objects. In the conventional fused filament fabrication sense, we are using a single spool of material and it has a single color, but with that approach, they can print some colorful prints. Now we will see the details. So this is quite weird. They are, as you see, printing the filament, which is to be used again in printing of another object. So now the filament is ready, so they will use that filament for the fabrication of a colorful object. Yes, that's it. If you use the conventional approach, this benchy will be in a single color, but right now it has many colors. So this is the conventional approach. And they do manual exchange of colors. There are also some equipment in market that, I'm sorry, yes, here. I think the name of the company was Palette. They input such materials, such colored filaments into a kind of their equipment and then extrude that color. But right now what they are doing is that they're printing a single spool of, let's say, colored filament and then using it for the fabrication of a specific product. Their disadvantage is that they cannot, for instance, use this colored filament for fabrication of another object. It's especially programmed for the printing of that benchy. So this is how they're doing. They have such inclined regions, try to make sure that the materials, the colored regions are stick to each other well. I have problems with my internet connection. I hope you are hearing me properly. But that's the main idea. Obviously, they need to have a proper, let's say, software. This is their simple software right now. They arrange the colors and they tell you when to stop and install a new material. But obviously, this is quite complicated. In the software, you select the regions of your part to be printed in different colors. And then their software, as you see, generates the regions for this colorful part. Any questions, guys? So I can continue with the rest of the chapter. I'm not going to spend time on this introductory part. We said that these extrusion systems should have some horizontal scanning equipment. They should be able to stop the extrusion, start it, from time to time. And obviously, since it's a layered manufacturing, they should be able to move upwards and downwards. We may do the extrusion by using some chemical materials which are used to melt the material or solidify the material. In the most conventional way, we use temperature control. So we said that there are some basic principles. What are they? We need to load the material by using some kind of pusher or maybe some pressure sources, or by using some pinchers, by rollers. Once you have an filament, with the help of these rollers, we push this filament into the heating chamber. And then in that heating chamber, we do liquefy the material and extrude it onto the bed. If it's the first layer, it will be extruded on the table, on the bed, and it should be sticking to the bed properly. Or if it's the next layers, then they should be stick to the previous layers. And obviously this plotting should be done in a controlled manner. The accelerations, the decelerations should be set properly. Otherwise, you may have some extra material all around. This will decrease the quality of your product. And sometimes, depending on the complexity of your part, you need to generate some extra structures to support these materials which are hanging in air. These are some details. We discussed that instead of having just pure filaments, you may also continue with directly granules, but there you need to have an extruder inside, this special screw inside your printer, and fabricate your parts accordingly. And we have seen an example of fabricating filaments. We start with granules or pellets, and then with the help of it, we can generate our special filaments. These are details for the liquefaction. We discussed extrusion process. We said that the flow on the printer depends on the pressure we are applying on the heating chamber, the nozzle geometry, the nozzle opening actually, the viscosity of our material, and the temperature. Since we know that the viscosity of the material changes with temperature. Then we said that solidification is quite important, since for dimensional accuracy, if you cannot satisfy the solidification properly, then your accuracy will be very low. The size that you will not be able to control the size of your products. Then we said that for the position control, for cheaper systems, we prefer to use belts and stepper drives, stepper motors, but for professional systems, we prefer to use lead screws and servo motors. This was an example of a novel technology for plotting systems. And we said that we prefer to use lower speeds while we are printing the outer profiles, since these are the things, these are the materials actually we will see once we have the parts. And for the interior, we can use higher speeds since we want to decrease the fabrication time, and since the interior is not visible, you can always use higher speeds. Another issue we discussed here is that we prefer to have as continuous paths as possible, since continuity will decrease the time spent on the fabrication, and also it will increase the quality. Since if it's a continuous path, then that means we are not stopping the extrusion or restarting it again. In continuous path, we will do it just once. We will start and then complete the whole layer and stop the extrusion. So with such an approach, we will not always have extra materials around, and the overall quality of the printer will be much better. And then we have discussed the bonding. Bonding is important, since if you cannot bond the layers properly, then if you have some shear forces, you can easily break your part maybe into some smaller parts. And you need to actually apply the required energy. We have a critical level for this energy. If you apply less energy, then you'll not be able to join them together, join these layers, since the previous layer will not be melted a little bit. But if you have high energy, applied energy, then that means the temperature of the previous layer might be increased too much, and we may melt more material. So that's another issue, and you will lose the dimensional accuracy. So the thing is that you should apply the required energy, not less or more. And we discussed the supports. So if you have some shallow angles or some overhanging parts, we need to support them from the underneath of these regions. And we said that if you have an angle of overhang angle of 45 or less, then that's fine. You don't need to have special angles, special support structures, I'm sorry, but if that angle, this overhang angle, is more than 45, you need to have support structures. But if you want to keep the quality of your surface, then it's better you decrease this angle. Otherwise, you will see some staircase effect on that surface. These are YHTs of support generation. You don't need to generate, as I said, for Y, for letter Y, if the overhang angle is equal to 45 or less than that, but if it's higher than that, you should generate. And in the CAM software, in like Cura, there are also some settings. You can change this setting, change this angle, let's say 45 to maybe 60 or 70, it's up to you. If you are accepting the low quality on these surfaces, then it's fine. And sometimes we have such bridges in this letter, as you see. And if you consider a layer at this point, after this part is printed, then your extruder will jump to the other island. And while going from this island to the other one, you may extrude some material in air. This is up to you. If you don't want to use any support structure, then again, I'm sorry, trying to open this tablet. So there are such options. You may not use support structure, but the thing is that, once you do the printing, you will have a kind of an overhanging parts, and you'll have such kind of a bend here. If it's unacceptable for you, then you may do your prints without using any support. But if this length is not too much, if the length of your bridge is, let's say, 1 centimeter, then you may try not using any support structures. Since with proper cooling, your printer may have less bending here. So this is a nice issue, and you may consider it while designing your part. So if the bridge length is not too much, then you may continue it without using any support structure.
Hocam bir şey sorabilir miyim?
Yes, Deniz, go ahead. Or Alptu, Deniz.
Deniz.
Yes, Deniz.
Orada support structure olsa bile iki ayağın arasında hala bana sarkma olurmuş gibime geliyor. Nasıl olmadan dümdüz olabiliyor köprü?
Do you mean if you have support structure or if you don't have any support?
If we have support structure, there is
No, since we have, let me draw it from top view. In the top view, we will have such support structures. It's quite difficult to draw. And on top of these support structures, you will be printing the part of H like this.
hala aralarda boşluk yok mu yani? Sanki boşluk var
Yes,
gibi.
but these are very little, just few millimeters. so your material will not be able to bend more.
Okay.
But we know that once you have support in that surfaces, your surface quality will not be as good as the surface quality you have here. You have little bumps due to the connection of your support structure to that surface. So your main motto is try not to use support structure as possible. So we will always be avoiding from using support structures.
Hocam, supportlar arasında kabul edebildiğimiz bridge mesafesinin bir miktarı var mı? Malzemeden malzemeye standart kullanabileceğimiz, yoksa deneme yanılma yöntemiyle mi yapmamız gerekiyor?
We have default values, and this default value is usually around some 3 millimeters. But if you want to try, you can change it in the advanced settings. It's not available in the default settings, but if you are interested, you may switch to open some extra setting parameters and try to play with them. But obviously, there are also some material properties are important. The viscosity of the material, the speed of your fans, the quality of your fans are highly important. If you don't want to, let's say, support this one underneath, then that means once you do the extrusion, this material should be solidified as soon as possible. And for the solidification, we should have more air flowing, and the temperature of the air should be as low as possible. So if you have proper force convection, then probably the quality of your bridge will be a bit better. But if it's longer, let's say 5 centimeters, then it's unavoidable. You should use obviously support structure underneath. But if it's around, let's say 2 to 3 centimeters, maybe by proper settings, you may avoid using support structures. But maybe if it's longer than 3, then for sure you should use some supporting structures underneath.
Teşekkürler hocam.
You're welcome. Yes, I'm not going to spend time on support structure. We said that there are 3 accordion types, and we had seen this example. We discussed path control, plotting operations, and we said that infill generation is the most complicated part in the CAM software. It's quite difficult, and there should be as continuous paths as possible. And the extrusion, we said that depends on many parameters like these. Yes, I think we were stopped at this point, but we just have 5 minutes, unfortunately. Let me go through it briefly. First of all, we have 2 names for the most popular desktop 3D printers. The first one is fused deposition modeling, and the other one is fused filament fabrication. And I said that this FDM is the trademark of the first company who actually invented this technology, Stratasys, but we prefer to use fused filament fabrication since this is the name given by the standardization organization, the ASTM. So we'll be using FFF or fused filament fabrication for the rest of the semester. And the first one, or the patented one, was invented in 1992 by Scott Crumb, and he established his company called Stratasys. But as I said, we'll be using FFF for the rest of the semester. And FDM is quite popular since the desktop versions are quite cheaper after the patent is expired. And another advantage is that it's one of the method giving you the strongest objects in terms of extrusion-based additive manufacturing systems. The other extrusion-based systems are producing parts having less strength. And the main drawback, main disadvantage of the method is that it's a bit slower compared to other additive manufacturing technologies, but it's still useful. We can print smaller parts or very large products. And in these FFF systems, we mostly use ABS material or PLA material. The first one is acrylonitrile butadiene styrene, or the other one is PLA polylactic acid. And I mostly use PLA. It's biodegradable and it's much cheaper than ABS. But the main disadvantage is that it has less strength compared to the ABS. And also another disadvantage of ABS is that you cannot print it without a heating pad. Since its sticking is quite difficult, you need to heat the bed to maybe around 70 degrees. Another issue, you may even need to use a special glue or ABS glue, or maybe some conventional glues might be used on your bed so that your part will be stick to the table properly. And here's some typical values from statistics company. The tensile strength, tensile modulus, the elongation is usually around, as you see. But depending on some variations of ABS material, it might be about from 3% to 6%. And the heat deflection, as you see, after usually around 70 degrees, it starts bending, so you cannot retain its shape after 70 degrees. Let's have a look at another popular material. As I said, the PLA material is usually good, and as I said, it satisfies most of your requirements. And I use for about 95% of the time PLA material. Is an enough strength, durability, not a perfect impact resistance, but as I said, it's good enough. And it's very useful for consumer products, some toys, some smoother layers. Another issue is glass transition temperature is a bit lower than ABS. So this is around, I think, as far as I remember, 50 to 60 degrees. So you shouldn't leave it under sun in summer times. Then probably it will lose its dimensional accuracy. But its flexibility is quite low. It has a quite brittle behavior. Another issue, obviously, this is not soluble in any chemicals in water, but it's biodegradable. I think in nature it can dissolve. I don't remember the exact date, but in some years I think it can be soluble. And this is the printing temperature. Another advantage compared to the ABS is that its shrinkage is less. In ABS, it's usually around 3%, but in PLA material is around 1%. Another advantage compared to the ABS, you don't need to have a heated bed. For most of the time, without using any heated bed, you can print PLA material. You can print it on maybe some tape, some special paper, but you don't need to heat the bed. And once you have all these settings, the temperature, the bed height, then printing is not that complicated as we have done in the previous week. In some seconds, in some minutes, you can do the printing.